Now this is a thing that I actually wanted to play with today. Now typically of stuff that's come from China, it all comes up wrapped up nicely in a box, but there's no information with it whatsoever. I don't actually think there's even a model number on here. Now what this is, it's a stepper motor driver board, and the job of this is actually to take in pulses, because basically the way that you actually make the stepper motor move to a position, you actually give it a number of pulses. And so there's an input here which is pulse input, there's another input which is direction, and then you've got something called ENA, which is an enable, to actually enable the stepper motor driver. So these these 6 connections here, these will go to your microprocessor or to your, the brain of your printer, and then the actual stepper motors will connect to here. And I can see the windings. We've got B minus and B plus, A minus and A plus, and then we've got a high voltage input which is 9 to 40 volts. So this voltage here is what's actually going to power our stepper motors, because I'm going to be running my stepper motors at 24 volts, or maybe even more. So just looking at this stepper motor driver, I've just noticed there's some dip switches at the top of it, and there's 6 of them down there. And there's some instructions. Now it says that bits S4, S5 and S6, they're actually used to control the current of the stepper motor. I think it's maybe the maximum current. Now I think the stepper motors that I've got here are I think they're 2.5 to 2.7 amps. So we've got to set up these dip switches to suit that motor current. Now we've got some other instructions here which are to do with something called microstepping, and again, I'm not exactly sure. I can't really give you much of an explanation about microstepping, but basically it allows you to get much finer control over the position of the stepper motor. So just looking at the instructions that came with my stepper motor, it says it's got a basic step angle of 1.8. So I'm going to guess if I divide 360 degrees by 1.8, that's going to give me the number of steps it would take to make my stepper motor do a full rotation. Now assuming that I've got that right, I'll just make a note of that. It says 2,880.
And treble 5, 100. Just
look at what you can want.
Oh, and that's a bad miss.
And it's not even in the ballpark.
Well, I'm afraid a couple of my YouTube subscribers detected some shenanigans going on with the last video I uploaded. So in response to their comments, I had to rapidly delete that video and yeah, pretend it never happened. So So what I actually did was I did something really silly. I think, what was it? I said that I wanted to divide 360, and I think I did divided by 1/8, which of course is completely wrong. Does that give a number something like 2880? Of course what I should have done is 360 divided by 1.8, which equals 200 steps. I don't know why I did that. I've got absolutely no idea. It's just one of those brain fart moments. So yeah, I'm sorry about that, and thank you to the subscribers that pointed that out. But it's just between you and me. Nobody else need know how stupid I am. So I'm sorry about my rather silly mistake, and I guess in kind of reparation for that, some kind of punishment needs to be inflicted. Well, the truth is I don't like gin. Particularly, I don't like this rhubarb gin, and I'm really not a big fan. I mean, it's pretty horrible, this Bombay Sapphire gin. So what I think it would be a fair punishment is I'm going to drink these 3 glasses of gin, and then I'm going to go upstairs and let my missus give me a jolly good spanking. Cheers. Ugh. Oh God. Ugh, hell. So in the basic mode of operation, if we send this stepper motor driver 2,880 pulses, my motor should do one complete revolution. It should turn through 360 degrees. But as I was saying, we have something called microstepping mode. So what I believe microstepping mode does is it allows you to, rather than doing one step, which is 1.8 degrees, we can actually step in smaller amounts than that. And I think this is telling me here what it will do. So you can actually do, you can do 1/4 of a step, 1/8 of a step, 16th of a step, or I don't know, what do you call it, 30 seconds of a step, 32, divide it by 32. So I'm guessing what that means is if we actually take our basic 1.8 degrees of step, which our standard stepper motor has, if we actually set this up for something like, well, 4 stepping, I'm guessing it actually, I'm guessing it would divide that number by 4, 8 or 16 or 32. So if we divide it by 4, that would give us a step angle of 0.45 degrees. So basically a 1/4 smaller. So again, in theory then, if we do that 1.8 and we divide it by 32, then again, I'm guessing that, well, let's do that. 1.8 divided by 32. That's a very small number. That's 0.05625 degrees. So yeah, I'm guessing that, well, I am guessing, in theory, if we set up this microstepping to something like 32, rather than having 1.8 degree steps, we're going to be stepping in 0.005 degrees. That's a tiny amount, isn't it? I guess we'll have to try that, see what happens, eh? Now here's one of my stepper motors, which is the NEMA 23. Quite a weight, and I'm sure you'll remember last time we separated it into the A and B windings. Now I don't think it matters whether or not we use the A winding or the B winding. I don't think it makes any difference. If we get it wrong, the motor will just run in the opposite direction. So the first connection, let's just connect this A plus and the A minus. So I'll do A plus first. Now we will connect the A minus. Trying to keep my hand out of the camera's field of view because it's got this annoying habit of focusing on my hand, and then well, I'm sure you don't want to look at my my hand. Yeah, sure you don't want to look at my hand. Yeah. No, I'm sure that'll do for a temporary. Now we need to actually provide the main power to the stepper motor driver, which is going to be we're going to be 24 volts in our case. So VCC first, we'll do that one. Don't want to get these the wrong way around, do we? Would be a bit disastrous. So we've got a couple of LEDs here. I'm not sure what they do. One says power, so I'm guessing that one's power, and the other one is alarm, but I don't know what the alarm is. So we've got, what the other things we've got? We've got ENA. Now I think ENA stands for enable. Now from the bit of information that I did find, we don't need to connect ENA. Although it's an enable, what it actually does is it actually de-energizes the motor. I think that this stepper motor driver, when it's not doing anything, it supplies a holding current to the motor, which means that if you wanted to spin it by hand, you couldn't do it. So when it says enable, what actually it means, it doesn't mean it enables the motor to run. It actually enables you to be able to move it by hand. So I don't think we need enable. Now we've got a direction here. We'll maybe connect that, but I really don't care which direction it runs in at the moment. So we'll leave that disconnected for now. And then the one that I'm interested in is pulse minus and pulse plus. Now it's expecting 5 volt pulses. So again, we need something to deliver pulses. Now, we're going to be getting the pulses from the control board when this printer's finished. But just for now, I think I think we'll just use a signal generator. That should be able to provide some pulses. Let's try that. Well, today we're going to be using this Escort EGC 3233 signal generator, and it's actually a sweep function generator. Now, I bought this quite a few years ago and kind of paid nothing for it, but I've never managed to find an instruction manual for it, and it's a little bit tedious to set up in that it's easy to get it wrong. All the push buttons on it are all the buttons on it are all multifunction. They all push and pull. So usually whenever I get this out of the drawer about every 2 or 3 years, it takes me about an hour of pushing and pulling all the knobs to figure out how to use it. So I suspect today won't be any different to that. First thing we're going to do is we're going to need an output, and we're going to use the 50 ohm output because I suspect that's got more drive current than the other output here, which is, yeah, it's 1 meg ohm. So we'll use the 50 ohm output. I think we'll use a green wire for our pulse, just to not to confuse it with the power wires. So we'll use green for pulse plus, and we will use a black wire for pulse minus. And it's expecting 5 volts. Now again, from memory, this signal generator, it produces an AC output, so what you have to do is you've just got to put a DC level on the AC output, because I don't want to send AC to this. So we've just got to fiddle about with this DC offset level. So we need the scope. Yep, that looks okay, it's not going minus anyway. Now I wonder what we've got our pulses set to. Now I think we've got it set to divide by 2, but there's a couple of settings here. You've got divide by 2A and divide by 2B, and I don't really understand what divide by 2A or divide by 2B means, because all the others just say like 1, 2, sorry, all the others see 1, 4, 8, 16 or 32. They don't say divide by A or B. So if anybody knows what the divide by A or divide by B means, let me know, because I don't know. Wouldn't it be nice if we had something to put on this motor shaft just to make it easy to see it turning? And as if by magic, here's something I prepared earlier. Now, very annoyingly, I designed this motor support bracket to have a little pointer on it there, and the first thing I did is I took this out of the printer and dropped it on the floor, and it landed on the edge of this pointer and broke it off. So I'm afraid I've just had to biro in a black line. You know, such is life, eh? It'd be interesting to see if this actually fits, because I'm still trying to find out or figure out what the clearances are and what the tolerances are of my printer. So I've actually made this to have 0.2 of a millimetre clearance. This disc here, it's got a hole drilled in it to suit this shaft, and I've actually designed it to have 0.2 of a millimetre clearance. So it'll be interesting to see if it'll either go on or it won't, and yeah, we'll find out in a second. So let's fix this onto here. Will that do? That'll do for one. Have we got any nuts that'll fit that? Probably not. Now, I'm sure by now none of you are actually expecting me to actually know what I'm doing with this. My videos aren't really how-to videos, as you've probably come to understand by now. I don't pre-prepare anything really. What you see is me playing with stuff for the first time, and usually I'm playing with something new that I haven't done before, because I've got a ridiculously short entertainment span. I get bored so easily. You know, I never become an expert in anything because I'm bored with any subject before I could become an expert. So when I say I don't know anything about stepper motors or delta printers and all the rest of it, unfortunately I really mean it. I'm doing all these things for the first time, and you're just with me at the workbench. But I do hope, I do hope that you're all, you know, shouting at the screen when I do something stupid. That would kind of please me, that you know, that you're saying, Chris, you're an idiot. Don't do it like that. Come on, place your bets. Is this disc going to fit on the shaft? I've got no idea. I guess we're going to have to try it, aren't we? There we go. Oh, it's going. Phew. Back of the net. What can you say? Back of the net. Right. Will it move? So we've got the I've got my benchtop power supply. What's that set to? That's set to 24 volts, and the current limit's set to 2.4 amps. I think that's set to maximum. Will it go any higher? Oh yeah, 3 amps. In for a penny, in for a pound. Let's plug the old terminals in. Positive, negative. Is anything lighting up? No. Oh, switch the power supply on. Oh! So we're supplying it with, oh, I don't know. Is that 1 kilohertz maximum? Or is that 52 kilohertz? I don't know. Let's put a scope on there. Like I say, I don't trust this thing. It does bizarre things, this frequency counter. That's my excuse. It's not me that's an idiot, honestly. Actually, it might be me that's an idiot. Okay, it's a fair cut. Right, what does the scope say? Glasses. Need glasses because I'm old. Acquire. Alright, okay. It is 5 kilohertz, 5.2 kilohertz. Just turn it down again. So you can see, well, you can't see it, you can see the scope pulse in there. Let me turn that off, we don't want you on. Get off. So we just so it's pulsing about once every half second at the moment, isn't it? Let's turn the frequency up. Well, you know, I'm quite impressed with that, but it doesn't take much to entertain an idiot, does it? Do we dare going a bit faster? Let's put it onto the 10 kilohertz setting. Oh, I'm a bit scared now. Oh, ah. Right, I guess what happened there is that we got quite quick, didn't we? I'm going to hold that down. Let's hold that and do it again. What did we get to? "24 kilohertz we're stepping out there. 27, 30 kilohertz, 34, 36, 38. Is it going to lose 40 kilohertz? Oh, there we go. So it looks like the maximum we can step this thing at is about 40 kilohertz, which is a hell of a speed. Well, it seems to be running alright in one direction, so let's just try connecting up this direction bit now and see if we can reverse the direction of it. It just takes a 5 volt input, so we're going to connect up this little, I think it's Farnell, yeah, this little Farnell stabilised power supply, so let's connect that up. So we need to connect up the direction minus, which is that one. Is that, no, wrong one, that one there. Oh. That goes to 0 volts in our power supply. Now this power supply, it's a Farnell's Tops power supply. I don't know if that's the model number, Tops one. But if you come across one of these on eBay, I'd actually say they're quite useful in that they've got a 5 volt rail on which you can adjust up and down a bit. They've got an overload protection on them, and they've also got a 0 and a minus 15 and plus 15. I think these were used a lot in schools for testing things like op-amp circuits. But I'm kind of guessing that I was after one of these power supplies for ages because it has the minus 15 and the plus 15 volt supply, again for op amps. But I guess that a lot of op amps that people are using today, they're you know, the single rail devices, aren't they? So maybe it's not so important to have plus and minus 15 volt power supplies. But again, back in the day, it was you know, it was very, very handy to have a minus 15 volt supply. Okay, so we'll just connect up the plus direction wire, 5 volts. And stick this into our power supply. And in theory, when I switch it on, it should change direction. There's the theory anyway. There we go. Oh, there we go, as if by magic. Let's go the other way. So hopefully we can probably do something a little bit more disruptive and annoying than that. Let's up the speed and make it reverse directions. Seems to handle that fairly painlessly actually, doesn't it? I've just noticed when you switch it off there is a little bit of a delay, and I'm guessing that's because there's capacitors in here that have to discharge. Tell you what, let's just dab the wire on and off, maybe that'll be quicker. Yeah, I'm sure we can be a bit more annoying. Let's make it go really fast and do it. Oh, So it's obviously lost sync there. That's interesting, isn't it? Will it go back? Slow it down and see if it catches up. There we go. Okay, so obviously if we reverse direction when it's actually running quite quickly, I'm guessing the fixed permanent magnet in here, which I think these have a fixed permanent magnet in, obviously it can't accelerate or decelerate quickly enough, so it's actually losing step with the rotating magnetic field, and once it's lost step it doesn't seem to want to get it back, so I guess we've got to slow it down and it'll resync. There we go. That's interesting, that, isn't it? So I wonder what the fastest frequencies we can make it reverse at. Not particularly fast. Yep. Okay, so obviously what's happening is, I say, it's losing steps, and once it's lost steps, it doesn't really want to get them back again, does it? Now I've noticed another little foible of this stepper motor. Well, I'm not sure if it's a stepper motor or the driver. I'm guessing it's this cheap stepper motor, but at certain frequencies it all seems to get a little bit upset. So if we just increase the frequency, and it is, I'm afraid, it's very crude, this the frequency control on this thing. So 100 Hertz is okay. Keep going up. But at around 100, it's anywhere between 130 and 142 Hertz. It all gets a bit horrible. Can you see this? It's just kind of jumping and it's going forwards, and it's always going in the right direction, I think. But is that what's causing that resonance? I don't know. Is that a fault in the stepper motor driver, or is it a fault with the stepper motor? I'm guessing it's probably the driver. I've never seen, when I've played with stepper motors in the past, I've never seen them having this problem. But is there certain frequencies stepper motors don't like working at? I don't know. Again, if you know, leave it in your comments, but it certainly doesn't like that. Yeah, it seems to be 143 Hertz. It really doesn't like that. Let's try going past it. Yeah, 100 by 140 Hertz, it's okay. Oh no, it's doing it again. Yeah, definitely doesn't like that, so I don't know what the answer is to that. Does anybody else know? Once you go past it, it's absolutely fine. And again, certain step frequency, if you go too fast, the motor just mechanically can't keep in step with a rotating field, and it just stalls. So obviously there's some practical limitations to what we can actually do with one of these stepper motors using this this driver. So at the moment we're using a 1-to-1 stepping regime. So let's just see what 100 Hertz looks like, and then what we'll do is we'll try putting it in a micro stepping mode, and it should turn slower. So let's find 100 Hertz if we can, roughly. Okay, so we're about 100 Hertz now, and this is about as accurately as I can actually set this. So Yeah, we're not microstepping at the moment. We're actually at a 1-to-1 step mode. So the next one is divide by 2. So let's just turn the power off and try that, and it should go slower. And it should also take smaller steps as well. On, off, on, off, on. So when we switch this back on, if my predictions are right, this should move at half the speed. Yeah, and I think that is about half the speed, isn't it? So let's divide it by 2. Let's try dividing it by 4. I've got to read these the right way around. Divide by 4 is on, off, off. So hopefully this is going to be slower again. Which it is. Let's try divide by 8 now. That one is noticeably slower, isn't it? Interesting to know how much torque this thing develops. Yeah, I can stop it by holding it. Now, from what I've read, one of the problems with microstepping is that you have less torque. So I'm just trying to get a feel for that. Okay, let's slow it down again. Let's go to 16 now. Divide by 16. That's really quite slow, that now. It feels about the same to hold it. Now the final microstepping range is going to be divide by 32. So yeah, let's try divide by 32. Which is all off. That's easy. All off. And that really is very slow, isn't it? And again, can we stall it out? Well, it doesn't seem to take any less force to stall it, but yeah, this test isn't very scientific, is it? I guess for comparison, let's go back to the divide by 2, because that seemed to work quite nicely. I'm really having to grab it with both hands. It's much harder to stall it when you're using much larger steps. That's interesting. It's just, there's nothing wrong with it. It's just vibrating at the moment. If you can hear a funny noise. Let's go back to the original, which is divide by 1. Yeah, and again, that's really quite hard to stop now. Now in operation, this stepper motor drive board does get quite hot, but again, I guess it's got a big heat sink on it, so it seems to work. I think for today, that'll probably do.
Thank you, sir. May I have another? Thank you, sir. May I have another?